And indeed, we have another talk on steering by Marcio once he's wired up. And he is.
All right. So this works. So, good morning, to all of you. So, first of all, thank the organizers for accepting this talk. All right, let's begin with that. So, my talk is going to be about two subjects, and I don't have a lot of time, but luckily, our previous talk already covered a little bit of something of things I'm going to say, so that should help us with the timing, right? So, these are the two things I'm going to talk about. They're not very related to one another, but you'll see. Well, let's see how it works out. So, first of all, we've seen, so Ranieri has shown it for me. Well, we can describe a Bell scenario using causal structures, right? So we can say that, well, a Bell inequality is basically saying that you get a correlation which cannot be explained by this kind of all classical causal structure, right? In which, of course, lambda is going to be, as usual, always this hidden or latent variable we don't have access to, right? And so, and this, in fact, this is the smallest thing we can do that actually gets quantum violations. And quantum violations means that, well, if you actually have a quantum state here, you get some results which you cannot get if you just assume classical variables, right? I guess we probably all know that kind of thing. And then, of course, if you trade that for a PR box, so that we get even post-quantum results and so on. Now, and basically, if we take this scenario and analyze and try to remove one of these legs here, one of these variables here, you don't really see any advantage anymore. You either, basically, if you remove the y, for instance, you don't get anything, no quantum advantage, or if you add more communication, you also get, then the classical thing can reach everywhere. You also don't see any quantum communication. For instance, those two examples, so this example here and this example, you don't have any quantum advantage anymore. And then what we're going to work with here is a classic / quantum version of these causal structures, in which instead of having all classical variables, we have a quantum variable here. So think of it as a state which we can tomographically describe. So we have access to that state in general. And then we ask ourselves, well, first of all, this defines steering, right? So if this cannot be written like this, if you need a quantum state up here, then the system is steerable, the assemblage is steerable. Then what if we do different kinds of comparisons? What if we add a communication here, so we allow this communication to happen, right? And basically, well, it's a quantum version of a very well-known process called the instrumental process, used in, well, basically situations in which you don't have the freedom to access the variables freely, like cancer research. You can't force people to smoke, or economics. You can't just change things in an economy. So you use these kinds of, well, the classical version of these things. And we explored, well, three variants of these structures. So this is the basic one, just to set us up. So this is the one where steering is defined. Then we compare so this unsteerable kind of assemblage with the, well, possibly steerable ones. And we also compare them with a classically generated correlation, but with some communication allowed here. So that's the comparison we made in this first, on this article here. Right. And just for completeness, we also define this final structure here, which has to include all the others, because then we have access both to a quantum state to generate correlations, also to communication. And if we think about it, well, these are some of their names. If we think about it, they have to be subsets of one another in a pretty clear way. So if I trade this classical correlation for a quantum correlation, it has to be more general. If I allow some communication here, which was not allowed here, it has to be more general. And of course, actually, this arrow here, this means that I'm allowing communication. I'm allowing some causal effect. This could, in principle, not be used. So this always a generalization. And by the same token, this one is also a generalization of these two here. So this has to be included into this and to this one, and this has to be the superset including everyone, right? And the big question that we asked was, well, what's the relationship between these two here, right? Or another way, if I want to see correlations between these variables, and I can use either a quantum state but no communication, or a classical form of creating correlations but do allow for communication here, what's better? What wins in this kind of comparison there? Right, that's basically the question that we asked. And what we saw was that there's no clear winner, right? So if we take a look at these sets here, so this local hidden state set here is the subset of everyone else. And these two, I don't know if this image is clear enough, but basically this, so this sphere here includes the LHS, and this quantum plane here, or ellipse here, it also includes the LHS, but they each are able to reach correlations that the other cannot reach, but none of them is a subset of the other, right? So we have incompatible and different kinds of correlations between these two here, right? So this one means this planar thing here, and this one is this spherical three-dimensional set here. Yeah. Always unobserved, yes. Yeah, always unobserved in all these cases here, right? And then that's basically what I'm going to say about this result. So there's a paper there, and we actually define a measure for how far away they are from this one-sided quantum instrumental set here, based on a robustness, meaning basically adding noise and how much noise you have to add to the system to get back to this place. And we actually see that this quantum plane here, this Q planar structure, is actually as far as possible from from this one-sided quantum instrumental, meaning, of course, this guy can get very far from this one, but this restricted guy here can get as far as this one below here. Or in other words, steering is able to generate such a strong correlation that even classical communication here is not really necessary to get that far from this first set here. Well, that's the first result we're going to talk about. Maybe if you have questions, you can ask them now. Maybe if I show this slide. Or then, of course, they can be in the... Oh, sure. This one here, right? Well, you can't really communicate X, right? So well, it's kind of hard to explain. It's easier to give some examples, but it's kind of hard to explain here what's going on. I guess it's going to be kind of tedious to give examples to everyone, but I can talk to you later, I guess. Yes. I mean, I didn't get what you meant. Oh, mean going from here to this? I really didn't get what you're asking. Mm-hmm. Mm-hmm. Yes. Yes. Yeah. It's a different. Yeah. It's a larger set. Yes. But very interesting. So meaning this side being also quantum.
So sorry, I did the same thing, but maybe we should keep it to like short questions about this at this point.
Yeah, we
and
can
have a longer discussion later. In the break.
So we haven't done that. If I've understood your question, we haven't done that. But then we can talk later. Maybe I'm wrong. Right. So the second topic, and all right, I have time, not too much. So it's about quite a different subject about causal nonseparability, and trying to build a resource theory, or going towards a resource theory in that sense. So I don't know how many of you. So last week we saw a lot of things on causality and on indefinite causal structure, which I guess not everyone has seen here. But well, if we take this example here, it's a simple looking optical experiment with a PBS here, so polarizing beam splitter. And if we follow these arrows around correctly, we see that a horizontal polarization goes first through this unitary A and then through B, and a vertical polarization goes first through B, then through A. I just have to follow them around. And interestingly, if you get a superposition of H and V of these two polarizations, we actually get a system in which you apply these unitaries in two different orders, and these two are in superposition, right? And I'm assuming these unitaries actually act on something that is not the polarization, right? So polarization is reserved to doing these paths here, and these unitaries act on, say, some spatial degree of freedom, something else that's not polarization, right? Which is what I just said. Now, we were going to work with something a bit more general, so instead of that, we're working with this, well, this is called the process matrix. Some of you know this very well, some of you maybe not, which is a way of generalizing mathematically the structure. So we have these two labs, which can do whatever we want, whatever they want to, but they actually have a very well-defined order. So these labs receive some input and send out some output. So, and this input is necessarily before that output. This is very well defined, both for A and for B. But besides that, we can have any different orders, including superpositions of those orders. So this output can be before this input or afterwards, and so on, right? And that's what I just said. And then we're going to the polarization there we're serving as a control variable. So this control here, C, this is usually omitted, but for us it's going to be important for our protocols later on. So I'm explicitly writing this out or drawing this out here. And the point will be to describe these I-shaped things, right? So these process matrices, irrespective of what goes on in these labs. So these labs are going to have the freedom to do whatever they want, given they have an input and an output. And we're gonna deal with these structures here, right? With the before and after each lab, right? And this causal nonseparability is actually a resource for doing quantum tasks, right? If you see, well, there's a few papers here by Quiribella, Araújo, Guérin, which basically say you have this kind of problem here. These two have some inputs, and you have to calculate a joint output. And you want to use as little communication as possible. And actually, if you use a superposition of communicating from A to B and from B to A, you actually see that you can use the minimum. You get to use less communication than if you didn't have this kind of superposition of A, B, and BA, right? So this is actually a resource for solving some quantum tasks. And we ask, what do we need to actually define a resource theory? So Ranieri has already defined the basic things. So I like to compare with entanglement. So we have the free states, which are separable states in the case of entanglement, or causally separable processes, which are basically processes in which you have either a well-defined order or a convex combination of that. So basically, if you flip a coin and that decides whether you go first A then B or vice versa, that's still not the resource. You actually need a quantum superposition of sorts. And it's interesting to discuss that in entanglement, we have the free operations are actually defined not just mathematically. There's a physical principle behind them. If those of you who were here last week saw a presentation by Julio de Vicente actually exploring different possibilities for free operations of entanglement here. And actually the choice of local operations in classical communication is a physical one. They're very implementable physically, but we could have different kinds of operations with entanglement. There's actually a wide variety of things that can come up if we trade these operations. And in fact, it's not very clear what should be the free operations for causal nonseparability. Of course, there's one property that has to be obeyed. So if you get a free state and you do a free operation on it, it cannot be a resource state. But besides that, there's still some room for to define things. Well, now, what we did was, first of all, we defined some free operations. So this should not be an exhaustive class so far. I mean, exhaustive in terms of what can be done. But some operations which are actually quite simple, and they should be free operations for all we can think of. So just to try to give you an idea. So we have some process matrix here. So we're going to transform it into some other process matrix. And here, of course, it's kind of a simple thing. If we apply unitaries to these inputs, we have a different process matrix which obeys everything we had before. It's not going to change anything very relevantly. Now, the point is, which free operations can we use in general that preserve this causal separability, including this example, but also more, right? And another thing, well, I'm going to get to that image later. So first thing we can do is, well, we can do local operations, right? So if we do operations that have no signaling, so no A to B signaling, so if we forbid that thing here, but we can allow this kind of thing, so signaling to the forward on each side. This is not going to change the order from A to B and from B to A, right? So this is going to preserve. This is going to be a free operation on this set. And actually, when I say it's not signaling, I should stress that we can actually use entanglement, right? So we can have some entangled state here, and this is used to entangle the new inputs that the labs receive. So this maximally entangled state, for instance, it can be used, and these are going to be entangled as long as you don't actually signal things to one another, right? So this is something that's included when we say there's no A to B signaling. This using ancillary entanglement is allowed, and so the name we have for that, well, kind of a temporary name, is basically that you have local operations assisted by entanglement. So this LOAE way of writing these operations, and then they have to be free, right? For any reasonable theory, they should be free, right? Of course, they are unable, because they're unable to alter this ordering. So actually, because they are unable to alter this ordering, actually we can do these kind of operations, actually do them coherently. So we can do any of these operations with any coherent control. This is not going to change this order in any way. So it's always going to be a free operation. Also preserved. So if people want to talk about the causal network itself, the causal network itself is preserved by this kind of operations. Now another operation is, which is not order preserving, actually doing a swap. So basically swapping one's inputs, and so the inputs of each lab and also the outputs of each lab. This of course changes the ordering from A before B to B before A, but this is still free. So as long as we respect some validity constraints, so we can't have just a single swap because this can generate a causal loop. We actually, if we do this kind of swap here from left to right and right to left, we can still preserve, and additionally we can actually do some form of control. So we can use that control variable to actually define whether we're going to do the swap or not, as long as it's an incoherent control, right? Because basically, so this guy here does not have the resource, and by doing an incoherently controlled thing, we basically swap this one for this one with some different probabilities, P1 minus P, but this form is still preserved. If we did something coherently, then we would break the free operation part. This would no longer be a free operation. Now, if we think about how we can compose these two. Now, if we think about it, these are relatively simple operations that we can do. Well, if we're not signaling from A to B and B to A, and if we're not, or if we're swapping both of them together, which basically amounts to swapping the two labs, well, someone who's used to it is going to be able to tell pretty straightforward, well, these should be free operations, right? These are kind of the first free operations that we can think of when we're dealing with this kind of subject. Now, the interesting thing is, with these simple operations, we can actually do some interesting things. Now, I'm going to define a few variables here. I'm sorry for that. I don't want to get too technical, but I do have to define these things here. So a quantum switch is basically drawn like this. You go either first to A, then from A to B, and from B to the future of these labs, or you go with a dashed line first to B, from B to A, and from A to the future, right? So, and these two are basically, I'm giving these names here to these two things, right? I'm omitting a lot of the actual definitions. Basically saying, well, this guy, so this 0 and 0 tilde means going first A, then B, and this 1 and 1 tilde means this process going first B, then A. Of course, there are more general processes that go first A, then B, or vice versa. This is just a simple example, such that we can write the quantum switch as this thing here. Right, as well, this expression here involving these zeros and these ones. And why am I defining these things? Because what we're gonna work with are basically what I'm calling imperfect quantum switches, in which instead of having a 50-50 superposition, we have some skewed superposition, possibly 99% here and 1% here, or whatever we want. And we're going to work on these. So the point is that if we had a 50-50, we would have what is a paradigm of these structures, a quantum switch. But if we don't, if we can have a skewed superposition, which we would imagine to be something less interesting, less powerful, less of a resource than before. And the first thing we show is that we can actually define quite specifically and operationally that these states have that some of them have less of the resource than the other. So basically, so if we compare these two, so this is a quantum switch with a 50-50 superposition, and this is a very skewed superposition, right? 90% here and 10% here. Intuitively, you would think, well, the second one seems to have less of the resource than the first one. So this is a superposition, this is a 50-50 superposition, this is very skewed. And we can define that operationally. Basically, if we do some of the operations we've shown, mostly acting on the control variables, we can actually show that we can go from any alpha beta to any other alpha beta if the probabilities associated with them obey majorization. Meaning, well, let me show that on a graph. If I have the 50-50 superposition, I can go to any other distribution that's closer to the edges. Meaning I can always move closer to the edges, and I can also go from one side to the other as long as the end result is closer to the edge than the previous result. Meaning the closer I am to the 50-50 result, the more resource I have. So I can go on the direction that these arrows show towards the edges, but not the other way around. So this substantiates a notion that we have intuitively, that this 50-50 quantum switch is actually more powerful, has more resource than others. Right? So this guy has a maximal causal non-separability. The other result that we have seen, I'm going to skip that. We don't have a lot of time. Basically, what we do is, just the idea of what we have to do. So we basically act on this control bit. So we do this measurement here. So if this first measurement, if we do this measurement here, if this first outcome comes out, we get exactly what we wanted. If the second one comes, we need the second one for that to be complete. If that comes out, we have to do a swap operation, which basically means we can do this if we do a measurement here and a controlled swap. But because this controlled swap is controlled incoherently, this can actually be done. So this is actually possible to do. This, we can generalize this a bit, but it's not very interesting for us right now. Now, distillation. This is the second thing that we can do, and this is particularly difficult in this scenario here when dealing with process matrices. And why is that? Because, the idea of a distillation is to get two copies of something, or two or more, right? And to find one copy with a lot of that resource, right? But using two copies of a process matrix is not a very simple feat. And why is that? Well, mathematically this shows up because when we have such copies of these things here, we have terms like these, where A goes before B times B before A, which are pretty hard to interpret, unless we do this thing here. We basically say that, A1, so the first copy we have A before B, and the second copy we have B before A, right? So, but what's the problem with that? Well, that seems pretty logical, pretty straightforward. The problem with that is that if we assume that, then we don't really have a lot of freedom in terms of doing joint operations on this A1 and this A2, or on this B1 and this B2, right? Because basically, what I'm basically saying is that, I actually have some figures here. Suppose we have two labs, and in the first of them, A goes before B, and the second B before A. Now I want to do a joint operation on A1 and A2. Well, this could be done if we had a scheme like this. Then we could do something together on these inputs or outputs. But then necessarily the B2 and B1 would be far away. I mean, far away means causally apart, and the structure such that we couldn't be able to do an operation here and here, a joint operation on these two. Of course, we can switch them, but this just shifts the problem around. We don't have this a lot of freedom to operate on these two, right? And these results are very well actually. So they have actually theorems on this showing how this is how impossible it is. In this paper, this was just recently on arXiv. And basically, but we can do this here because what we do, the only thing that we do jointly is act on the control qubits. So it's kind of a heavy image, but the point is that I have these two structures, and the only joint operation here is here on the controls, and then everything else just follows separately from one copy to the other, such that we can, and then in the end result we get one very causally non-separable process, and then another process which is just, just trash, right? Not resourceful, as we usually want in a distillation, right? And just to comment on some results. So there's actually a theorem we can show at least a lower bound of this rate. So if we have n copies, we arrive at n copies of something not very causally non-separable. We arrive at, well, less copies than that. So there's this rate r, which is at least equal to alpha square or beta square, the minimum of that. This is not necessarily optimal, so there might be better bounds on that. We can do distillation on average, just like Ranieri said. Well, if we take just 2 copies, we might just lose our state. But if we have 8 copies or more, we're going to be on average distilling. So we're going to be on average closer to the quantum switch than we were before. And we can actually define the distillable causal nonseparability based on this rate here, or on the optimal rate that could be done with this kind of process here. So concluding, well, first of all, we showed some class of free operation. It's really open. What should the full class be? And I mean, not just mathematical, but what should we choose to as free operations? But we got non-trivial results using them. So those were ordering. So to substantiate the notion of being more or less causally non-separable. And we also did distillation with a quantifier, and all based on that distillation. Well, thank you for your attention. Ooh, that was fast. It's a little off time.
Thanks. Any questions there?